Hello everybody, in this lecture we will be solving 2016 AMC 12B problem number 24. Here is a view of this problem. We have exactly 77 ordered quadruplets A, B, C, D such that the greatest common divisor of these four integers is 77 and the least common multiple is n. We are inquiring about the smallest possible value for this n. Let's begin with this condition here, this 77. So 77 is a multiple of A, B, C, and D. So therefore, I can make the following. Let A be equal to 77, because 77 divides A, right? So it has a 77 as a multiple, as is this one for B. 77 capital C. So the lowercase letters, I can replace them with the following. Well, the benefit of doing that is the conditions, these two conditions, the greatest common divisor and the least common multiple, now become, so therefore the greatest common divisor of capital A, capital B, capital C, and capital D now is 1, right? Because we removed the 77, which is the only common factor between these four numbers A, B, C, D. So we are left with four relatively prime numbers, and the least common multiple of these four numbers A, B, C, D would now be A, B, C, D. Now that we have removed 77 from each one of them, their least common multiple go down by 77. Indeed, we can go ahead and call this fraction as m. So therefore, recapping, the question which is asking for the smallest possible value for n, what I can do is I can look for the smallest possible value for m, and then I can simply multiply it by 77 to find the smallest possible value for n. One might wonder if the number of these quadruplets would change after we do this substitution, and obviously that won't be the case, right? Okay, so therefore, so far we're doing good. All we need now is to solve this system of equations, right? And now consider the following. So so let's have a look at this. Let P be a prime, B prime. And let's see for any prime in M, right? So let's see. Let P be a prime, and let also P to the K divide M. Let K be the largest power of this prime P that divides M. So how do I know it's the largest? Because if I look at P to the K plus 1, that won't divide M. That makes sense. So therefore, if that's the case for any given prime P which divides M, apparently the largest power of that prime that divides M is K, then what can we say about these four numbers? How can we find them? Well, obviously, our system of equations, so this is equation 1 and 2. 1 and 2 translates as the following. So 1 becomes the minimum of, well, so we need to express each of these in terms of, so for instance, this capital A, let's assume it has a prime alpha and then some other primes in it. This one, capital B, has P to the power beta and then some other primes in it. Let's see, capital C have P to the power gamma and then some other stuff in it. And finally D, right? So D has the same thing, right? So D is P to the power, say, delta and some other stuff in it. But so in its prime factorization, the power of P, that's same prime P, for A would be alpha and so on. Okay, so therefore what we want is, so from this first condition, number 1, the minimum of these four numbers, alpha, beta, gamma, and delta, right? Alpha, beta, gamma, and delta is, well, obviously it has to be 0. Why is that? Can you guys see why? Let me give, so you can pause the video, and at this moment you need to have a good idea why it must be 0. Indeed, it has to be 0 because if alpha, the minimum of alpha, beta, gamma, and delta is not 0, it means that all 4 of these numbers have a p in it, at least one p in it, and that violates this condition that their greatest common divisor is 1, right? So therefore the minimum has to be 0. And now the second point, the maximum of these 4 exponents, obviously the maximum has to be the same as the maximum of these 4 powers, alpha, beta, gamma, and delta, has to be equal to the maximum of the p inside M, right? But obviously this is, we decided M is equal to p to the k and some other stuff in its prime factorization, right? So therefore it has to be k. And that's it. So the question now reduces to solving and to finding the number of solutions to this system and setting it equal to 77,000, right? Obviously. Okay, so how many solutions? At this stage, we can come up with at least 2 different ways of counting. Let me provide you both of them. So probably the first one, so solution 1. We can do a casework basically. Casework. This one is on AOPS as well. The casework will be based on how many different values alpha, beta, gamma, and delta hits. So let's say that they hit, well, at the least they have to hit 2 different values, right? They have to hit 0 and k, obviously. If they hit 2 different values, then I have, well, obviously 2 choices for alpha, 2 choices for beta, 2 choices for gamma, and 2 choices. So in total we have 2 to the 4 choices, except, right, so complementary counting, except that we can't have a case where all 4 are 0 or all 4 are k, right? Does that make sense? So I have to subtract those 2. So that would give me 14. Okay, or alpha, beta, gamma, and delta can take 3 different values. Say 0, they can take the value k, and then anything in between 0 and k, right? So any I between, strictly between 0 and k. So how many, so how many in this case? Well, I have 4 choices for which one of alpha, beta, gamma, or delta will be 0. And then once I choose which one is 0, I have 3 choices for this guy. For one of them will be k, and finally the remaining one I have k minus 1 choices for oh, hold on, so 2 of them will be the same. All right, so let's first, so k minus 1 choices for the third guy, and then there will be 1 which will be repeated, and well, I have 3 choices for the repeating guy, right? Does that make sense? So that will give us 12, 36. 36 k minus 1. And finally, let's put it here. Yeah, why not? N is equal to 4. Well, all 4 take different values, basically, right? Alpha, beta, gamma, and delta take 4 different values. Obviously, that would be 0 and k. And then probably 0, I, j, and k, right? So you have 2 more values here, I and j as well. Okay, so let's see. We have alpha, beta, gamma, and delta. So we have, well, 4 choices for the 0. Either one of them will be 0. And then we have 3 choices left for the k. Well, we have 2 numbers to pick. We have k minus 1 choices for one of them, and then k minus 2 choices for the other one. Really, order doesn't matter, right? So does that make sense? As long as they are not equal to each other, right? I and j not equal to each other, and that's it. So we have 12 k minus 1 times k minus 2. I hope I did not mess this up. Okay, so that's therefore the total number of solutions to this system, number of solutions is equal to, we have 14 plus 36k minus 36, 36k minus 36, and then this monster here. So we have 12k squared, and then minus 2k minus 3k minus 36k, I guess, and then plus 2 plus 24. Okay, so plus 12k squared minus 36k plus 24. So that would give us well, plus 36k and minus, they vanish, and then yeah, we have 12k squared, and then 1438 minus 36. Okay, good. Plus 2 times 6k squared plus 1. All right, that's one way to count this. If you guys are not bored, we can also come up with solution 2. You can also count the number of alpha, beta, gamma, and delta satisfying these conditions, these two conditions. The minimum of these four numbers, alpha, beta, gamma, is 0, and the max of these four is k, using a principle of inclusion exclusion type of argument, which kind of seems more appealing to me. Well, obviously this number, whatever that number is equal to, well, it's just equal to the number of well, the four numbers alpha, and the number of ways to have this, right, between 0 and k. You can pick the four exponents of a, b, c, and d. However, this you need to make an adjustment, right? You need to subtract those cases which include 0 in it, right? So which which does not include 0 in it, sorry. So therefore, let's start from 1, let's say, alpha, beta, gamma, and delta, and it might include k, obviously. Or, I need to still also adjust, so minus the number of those that have 0, alpha, beta, gamma, and delta. However, they exclude k, so k minus 1. We don't want any solution which excludes k, right? Because we know the max has to be k. Similarly, the mean has to be 0. Otherwise, we discussed it earlier that the greatest common divisor won't be 1. And obviously, if the max is not k, then the least common multiple won't be m either, right? So therefore, this is not good. So that's why. But wait. So what I did is we removed those between 1 and k minus 1 twice. So I need to add it back at least once. Oh my. Does that make sense? So add them back at least once. And that's it. Now the rest is just counting each one, which should be okay, I guess. So the first one, we have four numbers, each between 0 up to k. You have k plus 1 choices here, k plus 1, and then 4 guys. So each one has k plus 1 choices, minus, now we still have 4 guys, so power 4, but we have k choices now. The same thing here, we have 4 guys, but k choices, minus k to the 4. And then finally we add back, we make final adjustment. We have k minus 1 choices for each guys. That's it. Let's cross our fingers. Let's hope we will get this expression again. So we have k to the 4 minus minus plus, they all vanish. And then we have a plus k cubed term, well, 4k cubed term, and then minus 4k cubed term, they vanish too. And then we have the k squared terms. We have 6k squared here, plus 6k squared, we have 12k squared. Oh, plus 4k here, minus 4k, they vanish too. Plus 1 here, plus 1, so plus 2. Factor out the 2, 6k squared, plus 1, and that is just beautiful. So we got the same thing. Now that's just perfect. So we know the total number of solutions, but this is just for one of the prime factors. This guy, this m, might have multiple of them, right? So let's see. So each of these obviously will have the same formula, right? So for instance, let's be more specific. Let's say that m can be written as p1, k1, p2, k2, p3, k3, and so on, right? So we don't know how many primes it has in it, and each one each one contributes this many solution, where so the number of solutions contributed and number of factors contributed are well, each one of these 2 times 6k square k1 square plus 1, 2 times 6k2 square plus 1, and so on. 2 times 6k3 square plus 1, and then 2 times 6k4 square plus 1, and so on. All right. Now let's see if we can get to that 77 monster, right? So what does 77 mean? Well, let's do it here, I guess. We can get closer to... Okay, so 77,000 is obviously 7 times 11 times 10 cubed, which is 2 cubed times 5 cubed. Aha! Okay, so now let's investigate. So we have this many divisors, right? We have this many divisors. Sorry, I meant to say quadruples, right? So we have this many quadruples, ordered quadruples, A, B, C, D, right? So let's do it here. Quadruples. And let's test different values for k1, k2, k3. So let's call it k. When k is equal to 1, how many different quadruples do we get? So by our formula, 2 times 6. Wait a second. Yeah, each prime will contribute this many to the count of quadruples. Each one have a factor of 2. That's strange. We have 2 cubed here. Oh, so that gives me the idea that there must really be 3 primes really. So m is really p1 to the power k1, p2 to the power k2, and p3 to the power k3. That explains each one will contribute that many to the number of solutions, number of quadruples, right? Does that make sense? So all I need to do is to account for the remaining number, right? So when k equals 1, we have 6 times 1 square plus 1. Well, I no longer need to worry about the 2's, right? Just focus your attention on, because we already taken care of the 2's. Well, or let's just keep it. Okay. So 6 times 1 square plus 1. So 2 times, what's that? 6 plus 1, 7. Okay. When k is equal to 2, we have 2 times 6 times 2 squared plus 1, which is 2 times 25, which is 5 squared. Aha, I like it. K equals 3, 2 times 6 times 3 squared plus 1, 9 times 6, 54 plus 1, 55, so which is 2 times 5 times 11. Let's go one more maybe. Because we don't know which case will benefit me, right? So 6 times 4 squared plus 1, which is 2 times 4 squared is 16, 96, 97, which is prime. And you can go on like that. Eventually, we need to pick 3 convenient ones that will give us the... You might think I'm already silly, right? So that does... Okay. I don't have to go further. Actually, I could have stopped after the first 3 steps, right? Because I have 1, 2, 3 2's. There you go. And then look at these 5's. I have 3 5's here already. And then I have a 7, and that's it. So therefore, the K1, K2, K3 are simply 1, 2, and 3. That's all. Okay, so because we want to minimize, find the smallest n is minimized if we minimize m, and then we can simply multiply by 77, right? So because I want to minimize m, the best, the minimum will be when the P1, P2, P3 are obviously 2, 3, and 5, and then the K1, K2, K3 are 1, 2, 3 obviously, but because I want to minimize this number, instead of putting them 1, 2, 3, I prefer to put them 3, 2, 1, and that's it. So 8 times 9 times 5, 8 times 5 is 40, 40 times 9 is 360. And finally, so this is the smallest, the smallest m, and in a similar way, therefore the smallest n is simply 77m, or which is equal to 77 times 360, And going back to the choices, 77 times 360 will give me 27,720, and this solves this question. Hope you enjoyed it, and looking forward to see you guys in our next lecture.